Welcome to UGC lecture series, BSc Physics Honors, Semester 6, Statistical Physics, Lecture 3. In this lecture, we are going to see thermodynamical functions of an ideal gas, classical entropy expression, then summary of these two concepts. Thermodynamical function of an ideal gas. You know, ideal gas is a gas which obeys the equation PV is equal to nRT. We know the various thermodynamical functions. In the lecture 2, we learnt the thermodynamical functions for a system. Now, we are going to express these thermodynamical functions for an ideal gas. The various thermodynamical functions are entropy, enthalpy, internal energy of a thermodynamic system, total energy of a thermodynamic system, pressure of a gas, specific heat at constant volume. These are all various thermodynamical functions. Now, for an ideal gas, these thermodynamical functions are expressed in terms of Partition function. You know, the Partition function can be given for three kinds of ensembles: canonical ensemble, grand canonical ensemble, micro canonical ensemble. Like that, three types of ensembles are there. Apart from these types of ensembles, many are there, but mostly used ensembles are these three. Now, the Partition function is a function which explains the partition of the energy level of a system, which explains the sharing of energy of a system to its entities. The grand partition function can be mathematically given as Z is equal to summation over n exponential of mu n by tau into Zn, where this Zn is the canonical partition function, where canonical is an ensemble type of ensemble. Taking into account the indistinguishability of the particles, the canonical partition function is written as Zn is equal to 1 by n factorial into h power 3n into integral of exponential of minus e of n over tau into d tau of n. This is how the partition function of the canonical ensemble can be written. This can be further simplified as f power n over n factorial. That f is equal to 2 pi m k t by h square power 3 by 2 into v, which is equal to 2 pi m k tau by h square power 3 by 2. This is the value of f in this equation. So, f power n comes here, no, the value of f is this one. Here the value of f is expressed in terms of the Boltzmann constant, relaxation time and Planck's constant. Now, the grand partition function Z is equal to summation over n exponential of mu n by tau into f power n over n factorial. Here this mu is the chemical potential of a system. This chemical potential explains the reactivity of the molecules of the thermodynamical system. So, chemical potential explains the reacting capacity of the molecule. So, the grand partition function is equal to summation over n exponential of mu over tau into f the whole power n by n factorial. Now, using the series expansion e power x, you know binomial series, that in binomial series e power x, e power minus x, 1 e power 1 plus x, like that exponential series can be expanded. Here that e power exponential of x is expanded like this, summation over n is equal to 0 to infinite x power n by n factorial. So, equation 4 may be written as this is equation 4, summation over n exponential of mu by tau f the whole power n by n factorial. Here that e power x concept comes. So, series expansion can be applied to this exponential of mu by tau. So, that equation may be written as z is equal to exponential of e power mu by tau into f. Keep this as equation 5. Now, we know this omega is equal to minus tau log z, where tau is the relaxation time, then z is the partition function. So, using this you can find the omega, where omega is the thermodynamical probability. In the discussion of probability, we learnt two types of probability, that is a priori probability, thermodynamical probability. The thermodynamical probability comes into picture when the a priori probability is not sufficient to explain the most probable case. So, here thermodynamical probability comes here using equation 5. This equation becomes that is the thermodynamical probability becomes tau is omega is equal to minus tau into exponential of mu by tau into f. This is the relation for thermodynamical probability, which is equal to minus tau into e power mu by tau into 2 pi m r by h square the whole power 3 by 2 into v. So, this is the expression for thermodynamic probability or thermodynamical potential. This is how you can get an expression for thermodynamical potential. This thermodynamical potential is one of the thermodynamic function in a thermodynamical system. So, here we are discussing the thermodynamical functions of an ideal gas. So, the thermodynamic function, thermodynamical potential of an ideal gas is given by this expression minus tau into e power mu by tau into 2 pi m tau by h square the whole power 3 by 2 into v. The next thermodynamical function is chemical potential per particle, chemical potential per particle, that is denoted by m or mu, either letter can be used to denote the chemical potential. We know n bar is equal to minus dou omega by dou mu when the volume and relaxation time are constant. Here this n bar is the average number of molecules in a system. So, this can be further explained as dou by dou mu of tau e power mu by tau 2 pi m tau by h square power 3 by 2 into v when the volume and the relaxation time are constant. So, here this function is partially differentiated with respect to mu. After differentiating this partially with respect to mu, we get this result, that is 2 pi m tau by h square power 3 by 2 into v, that is a constant. So, that constant comes as it is. Then e power mu by tau, here this is differentiated with respect to mu. So, e power x is differentiated with respect to x means we will get e power x. In the same way, here also, here we get 1 by tau mu. So, that 1 by tau comes front, that multiplied with the tau. So, the denominator tau and the numerator tau gets cancelled. So, tau does not appear in the result of the differentiation. We get e power mu by tau which is equal to minus omega by tau, Keep this as equation 7. So, this gives omega, that is thermodynamical potential. Omega is equal to minus n bar into tau. Keep this as equation 8. Substituting this equation 8, we get minus n bar tau is equal to minus tau into e power mu by tau into 2 pi m tau by h square power 3 by 2 into v. Further simplification of this expression gives the value of e power minus mu by tau as 2 pi m tau by h square power 3 by 2 into v by n. From this, we get the value of mu as mu is equal to minus tau log of 2 pi m r by h square power 3 by 2 into v by n. Here, the mu is in the exponential form. So, to remove this exponential, we need to take logarithm on both sides. When we take logarithm on both sides, this exponential term will get cancelled, only minus mu by tau will remain. Then this side, that logarithmic term will come. So, we get minus mu by tau is equal to log of this one. Then the denominator tau goes to the right hand side of the equation. We get minus tau into log of. So, here this whole term can be written as f. So, this expression is further reduced to mu is equal to minus tau into log of f by n. This is the expression for chemical potential of an ideal gas. This chemical potential is also one of the thermodynamical function. The next thermodynamical function is entropy. Earlier, first we have seen the thermodynamical potential or thermodynamical property. Next, we have seen the chemical potential, then entropy. The statistical entropy sigma is given by sigma is equal to minus dou omega by dou tau when the volume and chemical potential are constant. You know the definition of entropy. Entropy is the measure of disorderness of a physical system or thermodynamical system. Statistical entropy sigma is defined mathematically as the rate of the variation of thermodynamical potential with respect to the relaxation time. So, this is mathematically further written as dou by dou tau of tau into e power mu by tau into 2 pi m tau by h square power 3 by 2 into v when the volume and chemical potential are constant. Differentiation of this, partial differentiation of this with respect to tau. So, this term is constant. So, that comes out 2 pi m by h square power 3 by 2 into v comes out from the differentiation. Then this term alone differentiated. So, you got tau power 5 by 2 e power mu by tau when the mu is constant. So, the final expression 2 pi m by h square power 3 by 2 into v and dou by dou tau of tau power 5 by 2 e power mu by tau when the mu is constant can be differentiated as follows. That is 2 pi m by h the whole power 3 by 2 into V and minus mu by tau square into e power mu by tau into tau power 5 by 2 plus 5 by 2 into tau power 3 by 2 into e power mu by tau. This is how that differentiation will become after differentiating. This can be simplified further as 2 pi m tau by h square power 3 by 2 into V into e power mu by tau, that is exponential of the ratio mu by tau into 5 by 2 minus mu by tau. Keep this as equation 9. Now, from equation 8 we have the value of mu by tau, that mu by tau is equal to minus log of f by n, where f has some value in thermodynamics, which is equal to log of n bar over f, which is equal to log of n bar over f. Now, substituting the value of mu by tau, we get sigma is equal to, that is statistical entropy, sigma is equal to 2 pi m tau by h square power 3 by 2 into V into exponential of log of n bar over f, log of the ratio n bar over f into 5 by 2 plus log of f by n, log of f by n. This is how the statistical entropy will come. So, further simplification of the above expression gives 2 pi m tau over h square the whole power 3 by 2 into V into n bar over f into 5 by 2 plus log of f by n, log of f by n. This is the expression for statistical entropy. The final expression for the statistical entropy will be S is equal to K sigma. Statistical entropy can be related to the normal entropy as S is equal to K sigma, which is equal to n bar K log of 2 pi m k t by h square the whole power 3 by 2 into V by n plus 5 by 2 n bar k. So, this is how the normal entropy can be obtained from the statistical entropy. This equation is also called as the famous Sackur-Tetrode equation. Sackur-Tetrode equation which gives the normal entropy in terms of the statistical entropy. Next, we will see the expression for classical entropy. We know the entropy is the measure of disorderness in a system. That entropy can be represented by the letter S. So, let S be the entropy and omega be the maximum probability of the physical system assembly in a definite state. Then this entropy and the maximum probability of the physical system assembly in a definite state can be related by the expression S is equal to f of omega, where entropy is the function of maximum probability of the physical system assembly in a definite state. Now, consider two systems, two thermodynamical systems. Let us name the two thermodynamical systems as A and B, having entropy values as S1 and S2. The entropy of combined system will be S is equal to S1 plus S2, because entropy is additive in nature, but in some cases this additive nature is violated. So, there is a paradox in the entropy. That paradox is called as Gibbs Paradox. We will be discussing that Gibbs Paradox in the coming sessions. So, here the entropy of the combined system will be S is equal to S1 plus S2, and the probability of the composite system. Probability of the composite system in the sense you got a system A and system B, then probability for system A is omega 1 and probability for the system B is omega 2. Combination of these two systems, that is called composite system. Probability for the combination of these two systems is omega is equal to omega 1 into omega 2. Keep this as equation 3, where omega 1 is the probability of the thermodynamical system A and omega 2 is the probability of the maximum probability of the physical system assembly in a definite state B. Now, again S1 is equal to f of omega 1, and that means entropy of system A is equal to the function of system A. Then entropy of system B, that is S2, is equal to the function of system B. Keep this as equation 4. Substituting equation 1, 3 and 4 in equation 2. Equation 2 is the entropy of combined system. Equation 1 says the relationship between entropy and the maximum probability of the physical system assembly in a definite state. Now, substituting that, we will get f of omega 1 comma omega 2 is equal to f of omega 1 plus f of omega 2. Keep this as equation 5. Differentiating equation 5 with respect to omega 1, keeping omega 2 constant, we get omega 2 f dash of omega 1 omega 2 is equal to f dash of omega 1, where omega 1 stands for differentiation of the function. Now, differentiating equation 5 with respect to omega 2, keeping omega 1 constant. In the earlier case, we differentiated equation 5 with respect to omega 1. Now, we are going to differentiate equation 5 with respect to omega 2, keeping omega 1 constant. Now, we will get omega 1 f dash of omega 1 comma omega 2 is equal to f dash of omega 2. Dividing equation 6 by equation 7, omega 2 by omega 1 is equal to f dash of omega 1 by f dash of omega 2. In general, omega 1 f dash of omega 1 is equal to omega 2 into f dash of omega 2 is equal to omega 3 f dash of omega 3, like that it goes, which can be equated to k, where k is some constant. From equation 8, we have that f dash of omega 1 is equal to k by omega 1 and f dash of omega 2 is equal to k by omega 2, f dash of omega 3 is equal to k by omega 3. This is the thing we will get after differentiating the f of omega, where f of omega 1 is the probability for system A, then omega 2 probability for system B, omega 3, like that we can have many number of systems, the probability is omega, differentiation of that probability gives all these things. Now integrating above differentiation, we will get f of omega 1 is equal to k into log of omega 1 plus c, f of omega 2 is equal to k into log of omega 2 plus c. Now substituting this f of omega 1 and f of omega 2, we will get s is equal to f of omega, which is equal to k into log of omega c, k into log of omega c, where c is a integrating constant, and this integrating constant can be determined by some initial conditions. In case of a perfect order gas, that entropy S is equal to f of omega is equal to k into log omega. S is equal to f of omega, which is equal to k into log of omega, where k is the Boltzmann constant. This expression gives the entropy for a system, classical expression for the entropy of a system. So, from this lecture we learnt the thermodynamical function of an ideal gas, thermodynamical function like thermodynamical potential, entropy, chemical potential, all these things has been learnt from this lecture. Then the derivation of classical expression for entropy is done in this lecture. We know the definition of entropy. From the definition of entropy and the probability of a state to exist, we derived the classical expression for entropy in this lecture. After listening to this lecture, you can answer the following questions, that is, define thermodynamical potential of an ideal gas, give an expression for the internal energy of an ideal gas, what do you mean chemical potential? These questions can be answered after listening to this lecture. Thank you.